Okay, thank you. So I'm Gary Costa. I'm the project lead for the First Stars project, and I'm going to give you some brief update of some of the science that's been going on within our group. But first, I thought I should just remind you of the distinct themes that go on in First Stars. The first of those is to find and study the lowest metallicity stars in our galaxy and its neighbours. And then at the same time to compute detailed stellar atmospheric models and synthetic spectra so that we can measure abundances from those observed spectra. There is also programs to model the evolution of low metallicity stars and their supernovae as a function of mass and to determine their element productions and their yields of elements. And then we put that together to produce chemical evolution models of the Milky Way. And there's also a program going on of detailed computational studies of the formation of the first stars to investigate the role of conditions, such as magnetic fields, turbulence, angular momentum, and so on. Now, I'm not going to be able to talk to all of those themes in today's presentation, but I will give you a few highlights. The first thing I want to talk about is preliminary work by Nico Keegan and Alex Hager at Monash and Thomas Nordlander at the ANU about estimating the initial mass function of the primordial population, the metal-free stars. And their idea, their concept is to take all of the available observational abundance ratios for extremely metal-poor stars and compute the likelihood distribution for matching the observed abundances with the abundances predicted by the set of primordial supernovae models that are available from Hager and Woolsey. The supernova models cover progenitor masses from 9.6 to 100 solar masses, and they also have a range of explosion energy and different mixing scenarios. So then you can look at the combined likelihood distributions as a function of inferred progenitor mass and see what you get. Now, the underlying assumption here is that there's no chemical evolution. In other words, that every single observed low metallicity star, the abundances come from a single primordial progenitor. And so if you do that, you can make an attempt to reconstruct what the IMF might look like. The upper panel shows the distribution, likelihood distribution for 4 carbon-enhanced metal-poor stars. And if you see that for 3 of the stars, the likelihood distribution of mass is between, say, roughly 15 and maybe 40 or 60 solar masses. And for one star, J, 13, 44, 16, blah, 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 the likelihood mass range is a bit narrower, maybe between 25 and 40 solar masses. But for 1652, you can see that the likelihood distribution is very broad, but in fact actually does allow the possibility of progenitors up to masses as much as 100 solar mass, certainly greater than 60 solar masses. So that's the likelihood distribution for 4 individual stars. In the lower panel, we take about 100 carbon normal stars from the recent work that David Yong did, published last year, and again look at the combined likelihood, just a stacked likelihood distribution from each of the stars. And you can see that it is a very broad distribution. The median's perhaps around 25, 30 solar masses. But one thing it is fairly clear from this is that masses, progenitor masses in excess of 65 solar masses seem to be disfavoured, that there really isn't any abundance ratios in the current set of stars that we have that require an extremely massive star to produce them. Now, these are very preliminary results, and so I don't want you quoting them, but the approach is certainly likely to be informative, especially when we account for bias. It's unrealistic to assume that a star at -3 had a single primordial progenitor, but if we restrict the sample to lower iron abundances, we ought to be able to, in fact, make some more concrete assertions. What's going on? Next slide. And in that same kind of context, I should mention the work of Simon Campbell at Monash. He and his collaborators have been computing new models of stars of intermediate mass at very low and primordial metallicities. And again, they combine their results with a nuclear synthesis code to generate yields for a variety of different elements. And they find that for masses between 6 and 7 solar masses or more, the third dredge up, which occurs in the AGB phase of evolution, together with hot bottom burning, leads to the synthesis of very large amounts of carbon, nitrogen, and oxygen, and in particular with synthesis of large amounts of nitrogen, more than carbon, more than oxygen. Now, their results differ from existing studies, and unfortunately, I think that really just tells us that the physics behind mass loss and stellar winds in these stars, particularly in their late stages of evolution, and the treatment of convection in these stars really remain to be fully understood and modelled. But nevertheless, the results seem to potentially shed light on the origin of so-called NEP stars. These are nitrogen-enhanced extremely metal-poor stars rather than carbon-enhanced extremely metal-poor stars. Now, changing gears a little bit, I think one thing we've learned in the last, let's say, decade, that when you have large-scale spectroscopic surveys, you need really machine learning techniques to exploit those surveys to their fullest. And what you can do, in fact, is to use statistical techniques to isolate potentially interesting stars from the full data set. And an example of that is the work of Ardman Hughes, a PhD student at Macquarie, in which he used the TSNE statistical method to identify candidate extremely metal-poor stars in the roughly 600,000 star Galar data set. And in essence, what TSNE does is to group together stars with similar characteristics, reduces high-dimensional data down to a two-dimensional map where similar stars are close together and dissimilar stars are well separated. And so consequently, stars that fall near known EMP stars in the 2D map are also likely to be EMP stars. Now, there are two advantages to this approach. First, it's unbiased. Galar stars are just selected by apparent magnitude only, and so the candidate list can include main sequence turn-off stars that are generally excluded in giant focus surveys like SkyMapper. And it can also include carbon-enhanced metal-poor stars whose selection in photometric surveys like Pristina SkyMapper is best described as complicated. And the stars in Galar are also bright, and that means that if you find a particularly interesting target, you can follow it up, and in particular, you can study abundances that are not usually measured, such as nitrogen and oxygen, where you need to look in the near UV and in fact down to the atmospheric cutoff to get the oxygen abundances. Now, in Arvid's work, there's 75 stars in his sample for which there's no existing information on their metallicity. And what we've done, despite the best efforts of La Nina to wipe us out, is we've managed to get low-resolution spectra of all the 75 Galar DR3 EMP candidates with the WIFE spectrograph on the ANU 2.3 metre. And we've analysed those spectra in the same way as what we did with the SkyMapper program that was published, I guess, now almost 3 years ago. And we fit synthetic spectral models to get effective temperatures, gravities, and abundances. The first thing you can see is, looking at this graph, the red symbols are the Galar EMP stars, and the black stars are the work from the SkyMapper work, which has a much larger sample of about 4,500 stars. But you can see within the much smaller sample of the Galar ones, the metallicity distribution function agrees pretty well. You see the same very sharp decrease as you go to lower metallicities with a slope of minus 1.5 dex per dex, with the same very abrupt cutoff around minus 4, where stars become extremely, extremely rare, and basically there are only carbon stars beyond that metallicity. And so overall, the TCNE statistical approach has been quite successful. The contamination rate is low. Only 7% of the candidates actually turned out to have an abundance above minus 2, and that's again similar to the SkyMapper search value. The efficiencies are somewhat lower than the values in the SkyMapper search. The fraction with stars less than -3 is only 5% versus 18% for SkyMapper. And I think that difference is in part due to the fact of the brighter Galar magnitudes. A large fraction of all the extremely metal pole stars brighter than 14 are pretty much already known. And so, we were searching in the debris, I guess, for ones that had been missed previously. But overall, the results suggest that the statistical approach is valid, and so it can be applied to even larger spectroscopic surveys, such as Foremost, with the expectation of giving similar positive outcomes. One bonus, the first carbon-enhanced metal poor S-star identified in Galar DR3. Carbon CMP-S stars are carbon-enhanced metal poor stars that have very large overabundances in S-process elements. They're thought to be binary systems where you've had an AGB star that's transferred mass onto the star we see now and become a white dwarf. And you can see the very, very strong carbon bands and CH bands in the spectrum. And then if you go look this star up in Galar DR3, you see it has a very high barium abundance. Now, of course, there's probably lots of CMP-S stars in Galar. It's just that Galar doesn't really measure carbon very well, so you don't know that they're there. Two other quick things to finish up. Gaia DR3 is going to be released in a couple of weeks. Excitement. It's going to provide very low resolution spectrophotometry for about 200 million stars with estimates of effective temperature, gravity, and metallicity. But the spectrophotometry doesn't really distinguish very well at stars at or below -3. So if you really want the extremely metal poor stars, you've got to go and follow them up spectroscopically. And we're working with colleagues in Germany and Sweden to develop a method that will actually robustly identify candidates. And we hope to start observing those in a couple of weeks' time after the release and hopefully find some exciting stars. So that's a stay tuned. And the other one is that we have an ESO-accepted program to study nitrogen and oxygen in the lowest iron-abundant stars. As I said, we really don't know a lot about the extent to which oxygen and nitrogen are or aren't enhanced in the most extremely metal-poor stars. And you can see in the figure there some synthetic spectra computed by Thomas that shows that we do expect to be able to measure oxygen abundances as low as the solar ratio with signal to noise of 20 in at least half a dozen stars. And we have another application in for that in the current round. Okay, I'll stop there because I must be getting close to my time. And if anybody has any questions, I'd be more than happy to answer them. Thank you.